Hello everyone. Welcome to another episode of Deep Dive Knowledge. Hello. I'm excited to discuss your report on how machine learning can help materials informatics and enhance materials science development. Can you please provide an overview of the main findings and contributions of your study?
Certainly. The main findings and contributions of our study on how machine learning can help materials informatics and enhance materials science development can be summarized as follows. 1. Recognition of uncertainties. One of the key contributions of our study is the recognition of the uncertainties that arise in machine learning predictions, especially when models veer out of domain. We emphasize the importance of quantifying these uncertainties to ensure reliable and robust predictions. 2. Pathways for adaptive learning models. Our study highlights the potential for adaptive learning models in materials informatics. By systematically infusing new data, these models can progressively improve in quality, leading to enhanced predictions and insights. This aspect is critical for the further advancement of machine learning in the hard sciences. 3. Successful data-driven materials research strategies. We provide an overview of recent successful data-driven materials research strategies implemented in the last decade. These strategies demonstrate the effectiveness of machine learning techniques in accelerating materials discovery, optimization, and design. 4. Identifying challenges. Our study identifies the challenges faced by the materials informatics community and emphasizes the need to overcome them. These challenges include the acquisition of high-quality data, understanding data limitations, handling out-of-domain scenarios, and ensuring interpretability and transparency of machine learning models. 5. Future directions. Lastly, our study highlights the importance of addressing the identified challenges and suggests future directions for research in materials informatics. These include the development of robust and interpretable machine learning models, advancements in data acquisition and curation techniques, and the integration of physical principles with data-driven approaches. Overall, our study contributes to the growing field of materials informatics by providing insights into the potential benefits and challenges of utilizing machine learning techniques. It serves as a foundation for further research and development in this area, with the ultimate goal of accelerating materials science and discovery.
That's fascinating. I'd like to delve deeper into some of the specific points you mentioned. Firstly, in regards to the recognition of uncertainties in machine learning predictions, could you explain how these uncertainties arise and how they can impact the reliability of the predictions?
According to the report, uncertainties arise in machine learning predictions due to the statistical nature of these predictions. Machine learning models make predictions based on patterns and trends in the data they have been trained on. However, these models do not have perfect knowledge of the entire dataset or the underlying mechanisms governing the data. As a result, there is inherent uncertainty in the predictions. The impact of uncertainties on the reliability of predictions is significant. Uncertainties provide an indication of how confident we can be in the predictions made by the model. When uncertainties are low, it means that the model has a high level of confidence in its predictions. On the other hand, high uncertainties imply that the model is less confident in its predictions and that there is a higher degree of variability or potential error. Reliability can be compromised when uncertainties are not properly accounted for. Without considering uncertainties, users may blindly trust the predictions and make decisions based on them. However, if the uncertainties are high, there is a greater risk of making incorrect decisions or taking actions that may lead to undesirable outcomes. By quantifying and considering uncertainties, users can have a more comprehensive understanding of the limitations and potential errors in the Predictions. This allows for a more informed decision-making process, where uncertainties are taken into account to evaluate the reliability and confidence in the predictions.
Thank you for the clarification. It's clear that accounting for uncertainties is crucial for reliable predictions. Now, let's discuss the concept of adaptive learning models. How do these models incorporate new data and gradually improve their predictions over time? Can you provide some examples of how this approach has been successful in materials informatics?
Adaptive learning models incorporate new data and improve their predictions over time by continuously updating their model parameters based on the new information. This process is often referred to as iterative learning or active learning. In materials informatics, adaptive learning models can be used to improve predictions of material properties by incorporating new experimental or computational data. These models learn from the available data and make predictions, and then use the feedback from new data to update their predictions and improve their accuracy. One example of a successful application is the prediction of new materials with desired properties. Adaptive learning models can be trained on existing data of materials and their properties, and then used to predict the properties of new, untested materials. When new experimental or computational data becomes available for these new materials, it can be used to update the model and improve the accuracy of the predictions. This iterative process allows the model to continuously learn and improve its ability to predict material properties. Another example is in the optimization of material synthesis or processing conditions. Adaptive learning models can be used to make predictions about the properties of materials under different synthesis or processing conditions. By incorporating feedback from experimental data on the actual properties of the synthesized materials, the model can be updated and used to guide further optimization efforts. This iterative learning process enables the model to learn from the outcomes of different synthesis or processing conditions and identify the most promising routes for achieving desired material properties. Overall, adaptive learning models in materials informatics incorporate new data and improve their predictions over time by iteratively updating their model parameters based on feedback from new information. This allows them to continuously learn and refine their predictions, leading to improved accuracy and performance in predicting material properties and optimizing material design and synthesis processes.
That's fascinating. The ability of adaptive learning models to continuously learn and improve predictions based on new data is indeed a powerful approach in materials informatics. Now, let's shift our focus to the challenges faced by the materials informatics community. In your study, you mentioned the acquisition of high-quality data, handling out-of-domain scenarios, and ensuring interpretability and transparency of machine learning models as some of these challenges. Could you elaborate on these challenges and discuss their implications for the field?
Certainly. The materials informatics community faces several challenges that impact the field's progress and potential. These challenges include acquiring high-quality data, handling out-of-domain scenarios, and ensuring interpretability and transparency of machine learning models. Firstly, acquiring high-quality data is crucial for developing accurate and reliable machine learning models. In materials informatics, the data used in these models should be clean, curated, and reliable. However, obtaining such data can be challenging as it requires extensive experimental or computational efforts. Additionally, ensuring the data covers a wide range of materials and properties can also be difficult. Lack of high-quality data hampers the development of robust models and limits their predictive capabilities. Secondly, Handling out-of-domain scenarios is another challenge in materials informatics. Out-of-domain scenarios refer to situations where machine learning models encounter data points or materials that were not part of the training dataset. In such cases, the models may provide inaccurate or unreliable predictions. Handling such scenarios requires methods to quantify the uncertainties of predictions, especially when models veer out of domain. Developing solutions to handle these situations can enable adaptive learning models that progressively improve in quality by systematically infusing new data. This is crucial for the further development of machine learning within the hard sciences, including materials informatics. Thirdly, ensuring interpretability and transparency of machine learning models is essential for their widespread adoption and acceptance in the materials informatics community. Machine learning models often make predictions based on complex algorithms and patterns that are not easily explainable to humans. This lack of interpretability raises concerns about the reliability and trustworthiness of the models. Researchers in the field are working on developing methods to make machine learning models more interpretable and transparent, allowing scientists to understand how the models arrived at their predictions. This transparency is necessary for researchers to gain insights into materials' properties and phenomena, facilitating further discoveries and advancements in materials science. These challenges have significant implications for the field of materials informatics. Overcoming the data acquisition challenge will enable researchers to build more accurate and reliable models, leading to better predictions of material properties. Handling out-of-domain scenarios will enhance the adaptability and generalization capabilities of machine learning models, allowing them to be applied to a wider range of materials and conditions. Ensuring interpretability and transparency of models will foster trust in the predictions and facilitate the discovery of new materials with desired properties. Addressing these challenges requires collaborative efforts from researchers, data providers, and policymakers to improve data accessibility, establish standards for data quality, develop robust algorithms, and promote transparency in model development. Overcoming these challenges will undoubtedly enhance the effectiveness and impact of materials informatics, accelerating materials science development and enabling the discovery of novel materials with tailored properties.
Thank you for providing such a comprehensive explanation of the challenges faced in materials informatics. It's clear that addressing these challenges is crucial for the advancement and widespread adoption of machine learning in the field. Finally, let's discuss the future directions and potential areas of research in materials informatics. What are some key areas that should be explored to overcome the identified challenges and further enhance the field?